Hello friends, today we're going to continue our study of work, power, and energy by putting it all together into what is known as the law of conservation of energy. We're going to start by looking at an experiment to try to see what's going on and how energy can change form from one kind to the other. So we start off with a ramp, and I have a little sketch of the ramp on this worksheet, but let me show you a picture of the ramp and then a video. I said ramp. It's actually a series of ramps. There are 4 of them. You can see the red one, the green one, the yellow one, and the blue one. The question is this: if we release 4 marbles from the top all at the same time, or even at different times, the question is, at the bottom of which ramp will the marble be moving fastest? Not which one will win. That's a separate question. But the question is that I'm asking is, when will it be moving fastest? In other words, when will it have the most kinetic energy? What we're analyzing here is energy, right? And so if the marble has more kinetic energy, then it'll be moving faster. If all the marbles have the same, right, or if it's one marble, same mass, well, if they're all starting at the same height, then that means they all have the same gravitational potential energy. And also, when they reach the bottom, they should all have the same kinetic energy, no matter what path they took, whether it was the red, green, yellow, or the blue path, and getting from the top to the bottom. So let's see how this plays out. So here I'm setting up the 4 marbles, and then I'm holding a ruler, and then I release them all at the same time. And now let's look at how they land in slow motion. So you can see that they're all landing within about a ½ an inch of each other. There's the last one. Let's take a look at the physics behind this. First of all, how they're coming off of the ramps. Right here are the ramps up here, and then this is on a table, and there's the floor. So their horizontal velocity here, we'll call this VI, will determine how far they go. Because based on what we know about projectile motion, if they all start with the same initial velocity here, that initial horizontal velocity, then they're all going to go the same horizontal velocity this way. They're all going to take the same time to go this vertical distance down, right? And so based on that, that same time times the same initial velocity, they're all going to land in roughly the same place. And that's what we saw. They all landed in just about the same place. The ramps are a little bit funny. They're a little old. You know, here's a video of the condition of the ramps. So they're not too bad, but then down at the end, some of the tubing has come off a little bit. It's a little crooked. And so those are the kinds of things could also affect the velocity. So again, the idea here is that they all have the same initial height, right? This is the same for all of them. And so then at the end here, the question is, what is this final velocity? Well, mgh, they all have the same initial height, so the same initial potential energy should equal 1/2 mv squared. Notice also, if I divide by m, then the m's all disappear, and I end up with this expression that gh equals 1/2 v squared. If I want to find the final velocity, I can just solve this. So v equals the square root of 2gh. That's what the final velocity would be, if I know what the initial height was. And notice that the mass doesn't matter, which matches perfectly with what we know from Newton's laws. Right? So it all comes together. We know from Newton's laws that, you know, if you drop an object, the mass doesn't matter. The final velocity is going to be the same for any object because the acceleration is the same in the absence of air resistance, right? And we see that same thing happening here using this idea of energy, right? So that's part of the beauty of physics, is that we have these different considerations, but it all gives us the same result in the end. Beautiful. Okay, so what does the law of conservation of energy say? What are we talking about here? The energy at one point in the system is the same as the energy at another point, another time in the system, as long as there's no outside work being done. Okay, so in the absence of outside forces, i.e. work the total energy in a system remains constant. Okay, so that remains constant, and this means that energy is conserved, right? So energy is neither created nor destroyed. Destroyed in a closed system. Okay, so energy can get into a system from outside, right? Energy can shift forms from one kind to another, but that energy will always be conserved. In other words, we can always keep track of it. And then how is this law demonstrated by the marbles on the ramps? Well, the energy, the potential energy at the top equaled the potential energy at the bottom, so that no matter how those ramps moved, how those marbles went from beginning to end, which path they took, the kinetic energy at the end was equal to the gravitational potential energy at the beginning. What is the mathematical expression of the law of conservation of energy? Okay, here it is. This equation right here is the mathematical expression of the law of conservation of energy. So notice, we have two instances. It's always important that we take this. We've got 2 points, the initial point, the initial time, and the final time, the before and the after. And we have to just kind of like take photographs of those two spots, and then we're analyzing all of the energy there. So it's the initial kinetic energy plus the initial gravitational potential energy. So G is gravitational potential energy, I is initial. The initial elastic potential energy. Okay, so that's the initial state. What you do is you look at it and you say, what are the types of energy that are present? And you can calculate them. And what we can do is we can put them into this bar chart. I'm going to show you some examples. We use this bar chart to help us visualize what's happening with the energy. Now, the energy in a system can change if work is done from the outside. So we have the initial total amount of energy. That's all of these, right? So this is E total initial. Then there might be some work done. Right? Maybe somebody's lifting something, there's a machine that's doing some work, we don't know. Maybe there's some energy being lost somewhere, right? Again, from an outside force. All of that together should equal then whatever the final state is. And in the final state, we could have kinetic, gravitational potential energy, elastic potential energy. But another thing that can happen also is that we have a change in the internal energy of a system. Internal energy, we wouldn't call it a kind of mechanical energy, but we have to take it into account here. That would be from something like friction, right? So if you slide a book and it goes and it stops, well, where did the kinetic energy go? Friction slowed it down, and what happened was those two surfaces heated up a little bit. So thermal energy is a kind of internal energy. Another thing that could happen, you take an egg and you drop it and it breaks, right? So where did the gravitational potential energy go? Where did the kinetic energy go? It went into heating things up a little bit, not enough to cook the egg, and also into breaking it. So when you're breaking something, then you're also changing the internal energy of the system. And so there's always only an increase in the internal energy of the system. There's never a decrease in the internal energy of a system. Okay. So let's take a look at some examples to apply this. It says create an energy bar chart for a marble on a ramp if the ramp has a height of 0.15 meters and the marble has a mass of 0.01 kilograms, and find the final velocity of the marble. All right, well, the initial, it's always good to draw some diagrams and stuff. So here's a ramp, here's a marble, that's the initial position, and then this is the final. Okay, so at this point, in the initial, right, the before, what kind of energy do we have? Well, we have gravitational potential energy. It doesn't say it, but we can assume that the initial velocity is 0. Okay, I forgot to write that in there. Let's say the initial velocity is 0. So then all it has is gravitational potential energy. So mgh equals, let's see, and it has a mass of 0.01 kilograms times g, which is 10, and it's at a height of 0.15 meters. Okay, and then the kinetic energy, so what does it have at the end? It's gotten down to height 0, right? And so now all the energy has been transferred to kinetic energy, so K equals 1/2 mv squared. And now we can't calculate the kinetic energy because I don't know what the velocity is, but we do know that whatever the gravitational potential energy is, that's how much kinetic energy there is at the end. Gravitational potential energy we get when we do that calculation is 0.015 joules. Don't forget those are the units for joules. All right, so I go over here. Initially, there's no kinetic energy. It's not moving. We do have gravitational potential energy, 0.015. So I'm going to do this, and I can set the scale here. So I'm going to call this 0.005, 0.001, 0.01. Whoops, messed that up. 1.015, etc. Okay, so that means, and then there's no elastic potential energy, no work is done from the outside. So at the end, all of that is now kinetic energy. There's no gravitational, no elastic. We're assuming no friction. In the real world, there's always some kind of internal energy change, but we'll ignore that for now because it just makes things more complicated, right? We take the simplified version to learn it. So now I can solve for the velocity based on what I have over here. But what I'm going to do, I'm going to write mgh equals 1/2 mv squared. So mgh1, or the initial, 1/2 mvf squared, right? Because v initial is 0. I can cancel out m. So gh1 equals 1/2 vf squared. Now, 2gh1 equals vf squared. So vf is going to be the square root of 2gh1. So square root of 2 times 10 times 0.15. So I get 1.7 meters per second. Okay, so what are we doing here? We make a sketch, initial, final, and then we evaluate what kinds of energy do we have on this side? What kinds of energy do we have on that side? Was there any work done? We plug in the numbers that we know, we fill in the bar chart, and then we solve for the things that we don't know. So here's a similar example. The roller coaster examples are classic for energy. I made another video at one point solving a classic energy problem, which is a little bit more complicated about how much velocity is needed to make it through a loop if a roller coaster goes upside down. And so it says a 100 kilogram roller coaster car that has a velocity of 5 meters per second when it is at a height of 20 meters. What is the velocity of the car when it is at a height of 5 meters? Create a bar chart to help you solve this problem. So I didn't complete that first sentence. But anyway, we get the idea. So another roller coaster. So a similar kind of ramp. We don't know exactly what this looks like. But again, it doesn't matter. All we know is that there's a roller coaster car. At this point, it has a velocity of 5 meters per second. And it has a height of 20 meters. Okay, and then it gets down to a place where it's at a height of 5 meters. And we don't know the velocity. Okay, so initially, what do we have here? Initially, we have gravitational potential energy, UGI, so it's going to be mgh1, and there is initial kinetic energy, so that'll be 1/2 mv1 squared. In the end, there is also gravitational potential energy because it's still at a height of 5 meters. I'll call this HF. And then there is also final kinetic energy, 1/2 mvf squared. So when I write out this equation, I can write, right? So I'm following the model of this equation that's here. So Ki plus UGI equals Kf plus UGF. And now I can put in the formulas here. So Ki is 1/2 mvi squared plus mghi. That's equal to 1/2 mvf squared plus, and then ugf, I'm just substituting these expressions, mghf. Right. So now I can plug my numbers in. So this is 1/2 5 times 5 squared plus 5 times 10 times 20. That's equal to 1/2 times m, so 1/2 times 5. I don't know VF. And then plus 5 times 10 times 5. Okay, so those are my numbers. It's getting a little bit tight. We can see at least what we have for now right there. So the initial kinetic energy is 62.5, but I have to have a scale where I'm going up to 1,000. So the initial gravitational potential energy is 1,000. And so that means each of these is going to be 200, 2, 4, 6, 8, 1,000, right? And so 62.5 is actually going to be kind of short right there, 62.5. This is 1,000. So the total energy on this side is 1,062.5. That means the total energy on the other side also has to be 1,062.5. And we know that the gravitational potential energy is 250. So that's going to go like this. So 1,062.5 minus 250 is equal to 812.5. So that must be how much kinetic energy there is. So that is going to look like this. All right, so this is 250. This is 812.5. Okay, that's how much kinetic energy there must be at the end. Now I can go back over here. This is my expression for kinetic energy. And I know this is going to be, what do we say, 812.5 equals 2.5 times VF squared. So 812.5 divided by 2.5 equals VF squared. So VF is going to be the square root of 812.5 divided by 2.5. So that comes out to about 18 meters per second. Okay. Again, what did I do? I drew a sketch before and after. I looked at the types of energy I had, and I solved for the energies that I could. Put it into the bar chart to help me visualize what's going on, the transfer of energy from one to the other, keeping track of it. I see how much kinetic energy there must be at the end, and then I can use that to solve for the final velocity. 6. You take a small spring toy and compress the spring, set it on the table, and allow it to release. The 0.05 kilogram toy rises to a height of 0.4 meters. Find the velocity of the toy just before it lands back on the table, and find the amount of work you did to compress the spring toy. All right, let's do the first one, finding the velocity of the toy. So what's our initial state? Well, I compress it, I put it on the table, it goes up, comes down. If I'm finding the final velocity, I can use that height as the initial location, right, as the initial time. Because that's the one where I have all the information. I know the mass and I know the height, so I can find the gravitational potential energy at that point. I make that the beginning point. So here's the spring toy, something like that. It's been released, it's up high, and then it's coming back and it's hitting the table. So it's got gravitational potential energy here, and it's got final kinetic energy here. Okay, this is mgh I equals k, 1/2 mv squared. All right, so what's the information that I have? 0.05 kilogram toy, so 0.05 times 10, raises to a height of 0.4 meters. So it's equal to 1/2 0.05 VF squared. Okay, now I can take this and solve separately for v, right? Again, because it's just these two things, right? mgh is 1/2 mv squared. The m's cancel out. And I showed you before, v is the square root of 2gh. So this would be a quick way to solve for the velocity. This is going to be the square root of 2 times 10 times 0.4. This gives me 2.82 meters per second. So that's what the final velocity is. But to actually fill in the bar chart, I need to find out how much gravitational potential energy there is. And that is 0.2. 0.2 equals 0.025 times Vf squared. But I do know that the final kinetic energy is that, that same thing, 0.2. Right? So I set the scale, 0.1, 0.2. That's the initial gravitational potential energy and the final kinetic energy. All right, now, if I want to find out how much work was done in order to compress the toy, what I'm going to do here is I'm going to take when it's up in the air as the final state, right? Because I do the work, I set it down, the spring releases, and then it goes up high. The energy that it has at the end has to be equal to the elastic potential energy that I put into it by doing the work. So the amount of work I did is equal to the elastic potential energy, right? And so the initial state is me standing there holding the toy, about to compress it. Right? So that's the initial state, that's the final state. Now we already know, so here's U, G, F, and there's nothing, right? The energy here is 0. So we've got 0, 0, 0. We know that the final gravitational potential energy is 0.2. Well, then where did that come from? Because I did work. I did positive work on the system, and I gave energy to the system. Okay, so there's a summary of the law of conservation of energy, what the equation form of the law looks like, and how we can use bar charts to help us solve some of these problems. Thanks for watching. Don't forget to like and subscribe.